Akihisa, Okada from Toyota Central R&D Labs. He will give a talk on QUBO formulation using sequence pair with search space restriction for rectangle parking problem. So Akihisa, please start.
Thank you for your kind introduction, and thank you for giving me a chance to present my study. My name is Akihisa Okada from Toyota Central Research and Development Laboratories, and the contents of this presentation is recently published in IEEE Access, which is an open access journal. So if you are interested in my presentation, please read this paper for more details. To begin with, I would like to explain our perspective. We are application-oriented and interested in QUBO formulation and solver because of their potential to efficiently solve combinatorial optimization problems in engineering area. As you know, many combinatorial optimization problems can be approximately expressed in QUBO form. Since the QUBO problem corresponds to the searching the ground energy of Ising model, it is expected to efficiently solved by specialized solver like quantum annealer. Although the results in this presentation are obtained using simulated annealing, we believe that formulating in QUBO form is meaningful in anticipation of future development in quantum annealing. Here, we describe the problem we aim to address. The problem is a type of rectangle packing problem whose objective is minimizing the exclusive area when arranging given rectangles. The constraint is that the rectangles should not overlap. This problem is relevant to the application like warehouse storage or integrated circuit design. We explain the problem with this for rectangle example for more detail. We can consider the two arrangements shown here. The left arrangement occupies a width of 10 and a height of 6, resulting in an exclusive area of 60. The right arrangement has a width of 8 and a height of 7, resulting in exclusive area of 56. In this case, the right arrangement is more favorable for our objective. The rectangle packing problem is known as one of NP-hard problem, and efficient solution using QUBO formulation and solvers are expected. Therefore, we must determine representation and define binary variable and transform constraint as penalty term. First, we discuss representation of the problem. Here, we introduce a straightforward real space representation. This method describes the arrangement of rectangles by the position where each rectangle is placed. For example, the position of the rectangle is specified by the location of its bottom left corner, and so on. For this purpose, it is necessary to set up and divide the space. When rectangles are given, we need to prepare a space that is large enough for them to be arranged, and divide the space into size fine enough to describe the exact placement for the rectangles. For example, if we have a rectangle of size 11 and size 13, to represent their horizontal arrangement, we need to divide the space into unit of size 1. This line shows the division of the space. And in direct binary representation, the position of the rectangles will be expressed as 0, 0, 0, 0, 0, or 0, 1, 0, 1, 1. And in one-hot encoding, it will be represented like this. Thus, this method requires many bits. Moreover, for the expression of constraints, it is necessary to consider both the position and the size of rectangles simultaneously. The prohibition of the overlapping according to the position and size of rectangles makes objective complex, which can hinder finding the optimal arrangement. Thus, we adapted another representation for the sequence pair representation. The sequence pair representations sequence pair represents arrangement of the rectangles with two kinds of orders. First, I explained the encoding, that is a transformation from the real space arrangement to sequence pair representation. When this arrangement is given, a sequence pair can be derived by the order of line segment extended from the corner of each rectangles. Let me explain the first order gamma plus. Gamma plus is the order of the line segments when lines are extended upward from the top right corner of each rectangles. Like this. And if a line encounters a rectangle, like rectangle B, it is extended to the right and then up. Avoid crossing other line. The second order gamma minus is the order of line segment when lines are extended upward from the top left corner of each rectangle. In this case, if a line encounters a rectangle, it is extended to the left and then up. By this way, the sequence pair describes the arrangement of rectangles and they correspond one-to-one with original arrangement. This sequence pair can be represented in a two-dimensional grid arrangement called an oblique grid. By placing a gamma plus and gamma minus on the edge and placing the rectangles on the grid where the extended line from both edges match, A and A, the rectangle is placed here, and B, B, and C, and D. The sequence pair and oblique grid representation allow the arrangement to the expressed with simple discrete value for order, and since it is based on the arrangement of non-overlapping rectangles, there is no need to care about constraints related to overlapping rectangles. Therefore, it is considered suitable for representing the rectangle packing problem in QUBO format. Conversely, when an oblique grid is given, the original arrangement can be decoded. By placing the start and termination point on the left and right of the oblique grid, and tracing the rectangles within a 90-degree range to the right, the relationship between rectangles in the width direction of the original arrangement can be observed. For example, this solid line ABC corresponds to this line, and this dashed line AD corresponds to this line. Tracing the rectangles within 9-degree range, 9-degree range to the right means that we cannot trace D after B, because if we choose a B, D is not placed in the right 90-degree in this range. By placing the start and termination point on the top and bottom of the grid, oblique grid, and tracing the rectangles within the 90-degree range upward, the positional relationship in the height direction can be traced. From these two relationships, the original arrangement can be decoded. It should be noted that when tracing rectangles on the oblique grid, considering the width and the height of the rectangle as a weights, the longest path becomes the width or height contributing to the exclusive area. In this figure, the solid line corresponds to the longest path. This is longest path in the width direction, and this is the height direction. This rectangle have a large height, so the weight of this rectangle is big. So this is the longest path. The original problem we are interested in is finding the arrangement that minimizing the exclusive area. Thus, our goal is to finding the sequence pair having the minimum exclusive area, and this exclusive area is calculated by the longest path on the oblique grid. Now, based on the concept of sequence pair and the oblique grid, we would like to introduce binary variables for QUBO formulation. Let me explain the variables with this example. Consider a 3-dimensional extended oblique grid where an index for the rectangle is added to the oblique grid. And let this 3-dimensional diagram as let this diagram be the binary variable x. The ijk component of x takes the value 1 when the rectangle k is at the ith position on gamma plus and jth position on gamma minus. Otherwise, this x takes 0. Additionally, we introduce a new auxiliary variable y and z in order to calculate the exclusive area from the width and height of arrangement. The rectangles contributing to the longest path on GH and ZV in this example are shown like this. This line corresponds to this line, and this line corresponds to this line. We define the variables y and z to describe only the rectangles contributing to the width and height of exclusive area. The y pick up only the rectangles contributing to the width of the area, which are composed of parts of rectangles taking the value 1 in X. Y can take 1 from the X. And Z pick up only the rectangles contributing to the height. When we can correctly introduce such Y and Z, the width and the height of an arrangement can be written as follows. Here, WK and HK are the width and height of rectangle K. Next, I would like to explain the constraint that should be imposed on these introduced binary variables. First, regarding the variable X, it must be in one-hot representation for each index by definition. The second constraint is that since Y and Z represent the rectangles contributing to the longest path, the indices where Y and Z takes the value 1 must also have X taking the value 1. On the other hand, even if X takes the value 1 for an index, if the rectangles do not contribute to the longest path, Y or Z do not need to take the value 1. This feature is represented by these inequalities. The third constraint is that Y and Z represent the rectangles contributing to the width and height by being selected from the right 90-degree on GH and upper 90-degree range on GV. Therefore, rectangles that are not placed in this range cannot simultaneously take the value 1. The index condition can be written in like this, although a bit complex. In this slide, I show the QUBO form of constraints and minimization term for sequence pair representation for rectangle packing problems. First, HA is a penalty term for the one-hot constraint for X. And next, HB is a penalty term for the relationship between Y and Z for X. And when X is 1, it does not matter whether Y and Z is 0 or 1. However, in the case that X is 0 and Y and Z is 1, this penalty is imposed. The relative position penalty is written by this HG term. In addition to these constraint terms, we have minimization and maximization terms. As Y and Z must represent the rectangles on the longest path of arrangement, so we include the term H longest. Moreover, the original problem of minimizing the exclusive area is considered as H area. In usual procedure, finding the value of X that minimize the sum of these terms correspond to finding the arrangement that minimize the exclusive area. However, we have contradictory relation between the term for maximization and minimization terms. These two terms are related in that they seek to maximize the perimeter of arrangement while minimizing the exclusive area, which can sometimes be conflicting. In fact, when comparing these two arrangements, the term H longest related to the longest path is smaller for the arrangement on the left. while the term H area related to the area is smaller for the arrangement on the right. Therefore, the arrangement obtained by minimizing the objective function changes depending on the weight of these terms. Although it is possible to explore coefficients that select the longest path while minimizing the exclusive area, it would be difficult to determine universal coefficient set that are independent of the problem. Thus, another approach should be considered. Then we adopt a mitigation strategy for the contradictory relation by utilizing certain characteristics specific to some QUBO solver. Several QUBO solvers, including D-Waves, quantum annealer, can obtain multiple candidate solutions by repeating calculations in a short time. We then confirm the distribution of these candidate solutions. To group these solutions, we introduce the following parameter K. This K representation represents the number of rectangles on the longest path. For example, for this arrangement, K is 4. We confirm the K dependence of candidate solution for the pseudo-feasible solution, in which one hot and xy and zx relation constraints are satisfied. This distribution of solutions in H area and H longest space is shown in these figures for n equal 4 Ks. The optimal arrangement is represented by this triangle marker. From this figure, parameter K can be seen as a parameter that limits the search space and guides solution around the optimal solution. Since K means the number of rectangles on the longest path, it is expected that it will be possible to estimate the optimal K value in advance. Now, let me summarize the terms we have discussed so far and introduce the whole objective function in QUBO. The Greek letter from alpha to eta represent weight coefficient, and HABG are terms derived from the constraints. And H longest is a term for selecting the longest path on GH and ZP for sequence pair representation. And H area is a term for minimizing the exclusive area. And the final, the HK hot term guides the number of rectangles on the longest path to K. Now I will present the result of the numerical calculation. To begin with, I will present the result of a preliminary experiment to obtain the optimal K. We consider the optimal K would bring the highest proportion of solutions satisfying all constraints with a fixed number of samples. This plot shows the top 3 frequencies of K value for the calculate for problems with varying numbers of the rectangles n. As expected, K increases with the number of the rectangles, reflecting that it corresponds to the number of the rectangles on the longest path. In this plot, the circular marker in the right-hand figure plot the circular markers in the right-hand figure, plot the most frequent k value against the number of rectangles. By adapting the square root approximation, we obtain this dashed line result. These cross markers represent the integer value of these approximations, which we use as optimal k value in the subsequent analysis. Here are the instances of the problems we solved are shown. We started with problems involving four rectangles and incrementally added new rectangles, solving problems with up to 10 rectangles. As our formulation requires n cubed bits, a size that is difficult to handle with the current D-Wave quantum annealer. Therefore, we performed the calculation using simulated annealing instead of quantum annealing. Here are the arrangement which have the smallest exclusive area we obtain. There are instances such as from 8 to 9, where the adding just one more rectangle significantly changes the arrangement. And compared to the previous research, our solutions show improvement in all instances except in 8. We note that the previous study introduced sequence pair but did not care contradictive relation. I will summarize my presentation. We tackle the rectangle packing problem to find the arrangement that minimizes the exclusive area for given rectangles. We adapted the sequence pair representation, which handles discrete value of order and has the advantage of not needing to consider rectangle overlaps. However, there is a contradictory relation between obtaining the longest path on body plate and minimizing the area using sequence pair. To address this problem, we introduced a soft constraint term related to the number of rectangles on the longest path, leveraging the sampling solution of QUBO. This approach allowed us to achieve arrangement with smaller areas compared to the previous study. Thank you for your attention.
Thank you, Akihisa. Any questions or comments?
I have a question, if that's okay.
Yes, please.
Of course.
Yeah, a very nice talk. Thank you very much, Okada-san. So I like this method of, I guess it's encoding your problem into the sequence pair and the oblique grid technique. That seems very efficient way of handling the problem. I wonder if it can be applied more generally, or is it specifically for this rectangle packing problem, or do you think there are other combinatorial problems where it might be a useful tool to help encode things more efficiently?
In this sequence pair representation, we can treat the arrangement of the rectangle. So there is a possibility to we can apply to the time scheduling problem. Like I don't know in detail, but there's a possibility that the time scheduling is like a place arrangement problem.
Good, thank you very much. Thank you.
Any other questions? So I have a question. I'm also wondering to extend to apply this technique. And my question is, do you think, can you think about more complex problems? For example, from the natural expansion of this problem is, let's say, so if the rectangle 1 and 2, they want to be aligned together, and 1 and 3, they don't want to be aligned together. They want to be placed far away. So do you think such kind of constraint or any other constraint you can think about to introduce to the current formulation?
No. In such a constraint, for example, the two rectangles must combine.
Align or press together.
Press together. Is in single pair that we can treat the order. So I don't know the order of the binary variable, but we can. I don't know whether it's QUBO or higher order. So I don't know, but there's a possibility we can treat such a constraint. It's very interesting point. Thank you.
So basically, if the order, the horizontal or vertical, the neighbor order should be aligned together. Is correct?
Yes.
I mean, so let's confirm with the current situation. So, yeah, so we can take a look at the oblique grid. So, for example, A and B in a, so A and B always.
So, the order must, for example, the A and B, if we want to neighboring the A and B, the A, the D cannot intersect this order. So such a penalty will be imposed.
In other words, we see the A and C always, so it's separated. There, A and C are separated. And if we take a look at the sequence, A and C are always separated with other characters. That we can take into account as a cost function. That is what you say?
Yes.
It's here. Oh, that's interesting. Okay. Any other questions or comments? If not, thank you again, Akihisa. Great presentation. Okay, so I'd like to close this seminar. Thank you. Have a good day.